So let's look at the first of two examples involving Graham's law. So this is a question which says, if compared under the same conditions, how much faster than helium does hydrogen diffuse through a tiny hole? All right. So first thing I'm going to do is write down Graham's law in relation to these two gases, right? So basically, I'm going to write down here that the rate of effusion of hydrogen, remember now hydrogen exists as a diatomic molecule, divided by the rate of effusion of helium is equal to the square root of the molar mass of helium divided by the molar mass of H2. All right? So remember there's an inverse square root relationship between these two gases, right? Now, what I'm going to do, of course, is look up the molar masses of helium and the molar mass of hydrogen. So, according to the periodic table, the molar mass of helium is 4.00 grams per mole, or AMU. It doesn't matter which unit you use. And then for hydrogen, the molar mass of H2 is 2.016 AMU. And then we work that out. Let me put that here. So, let me get my calculator. All right, so we're going to divide 4.00 divided by 2.016 and then find the square root of that. And according to my calculations, this works out to be equal to 1.41. All right? And there will be no units because the units will cancel out. So basically, we can rearrange this to get the rate of effusion of hydrogen is equal to 1.41 times the rate of effusion of helium. All right? So what this is telling us is that the rate of effusion of hydrogen would be 1.41 times as fast as the rate of effusion of helium. So I would finish off answering this question by saying that hydrogen will effuse 1.41 times faster than helium. And that completes the answer to that question. All right? Okay, so that's the first example. Now, the next example is a bit tricky because in this question, let me go back to my pointer. In this question, it says 1% of a measured amount of argon, which is a gas, escapes through a tiny hole in 77.3 seconds. 1% of the same amount of the unknown gas escapes under the same conditions in 97.6 seconds. So the question is asking for you to calculate the molar mass of the unknown gas. Now in this case, they did not give us any information about the rate of effusion. They gave you, however, information about the time of effusion of the different gases. And at this juncture, I want to explain the difference or the relationship between the rate of effusion and time of effusion. And basically, the relationship is an inverse relationship. So basically, the rate of effusion will be directly proportional to 1 over the time of effusion. And if you think about it, it makes sense. If something has a faster rate, it doesn't matter what we're talking about. We could be talking about the rate at which a car travels, for example. Then basically that means that the time it will travel over a certain distance will be very short or be very small, right? If the rate is longer, right, or I should say if the rate is less or slow, that means that the time, hold on, if the rate is, what did I say? Well, if the rate is slow, that means that the time that it will travel, okay, I'm blanking out. If the rate is higher, the time of travel would be short. If the rate is slower, that means the time of travel will be longer, okay? So that shows you the rate relationship between rate and time, all right? It's an inverse relationship. Now, the reason why I mentioned that is because we already know that the relationship between rate and molar mass is an inverse square root relationship. So in the case of the relationship between argon and the unknown gas, we can write down this relationship. The rate of effusion of argon, oh shoot, same thing is happening again. Okay, let me try it down here. The rate of effusion of argon divided by the rate of effusion of the unknown gas would be equal to the square root of the molar mass of the gas divided by the molar mass of the argon. All right? Now, because we know that there's an inverse relationship between rate and time, we can add another part to this equation here, which says that the time of effusion of the gas divided by the time of effusion of argon would be equal to both of these terms right here. So what we really need is this relationship right here in order to solve the problem, because the question gives us the time of effusion of the unknown gas, which is this. The question gives us the time of effusion of argon, and we can look up the molar mass of argon in the periodic table, and then based on that information, we can determine the molar mass of the unknown gas. Now, the first thing I would do, based on my recollection of mathematics from back in the day, if we want to get rid of the square root sign, what we'd have to do is square both sides. So if we square both sides of this equation here, we're going to end up with the molar mass of the unknown gas divided by the molar mass of argon, and that would be equal to the square of the time of effusion of the unknown gas divided by the time of effusion of argon. All right? Oh, shoot. I'm sorry about this, folks. Okay. And then we can rearrange this to solve for the mass of the unknown gas, the molar mass of the unknown gas. That would be equal to the molar mass of argon times the time of effusion of the unknown gas divided by the time of effusion of argon, all squared. And then we put the numbers in. So the molar mass of the unknown gas will be equal to the molar mass of argon, which we can get from the periodic table. That would be equal to 39, write it here, 39.95 grams per mole, multiplied by the time of effusion of the unknown gas, which is, according to the question, 97.6 seconds, 6 seconds, divided by 77.3 seconds, squared. The second units will cancel out, so all we have to do is do the number crunching on my calculator. So that would be 97.6 divided by 77.3, and then we square that, and then we multiply by 39.95, and according to my calculation, this works out to be equal to 60, okay, we have to round this out to 3 sig figs. So this would be 63.7, and the units would be grams per mole, all right? Let me just check this again just to be sure. 97.6 divided by 77.3, and then I square it, and then I multiply by 39.95, and yep, that's what I got, 63.7 grams per mole, all right? So that's basically how this is done, all right? Okay, so the next topic, and this will be the final topic in this chapter, we're going to talk about the difference between ideal gases, which is what we have been discussing all along, and real gases. So until next time.